Okay, welcome to the second lecture of me and the third lecture of this course. So I will start right away. I'm sorry it was a bit late. I was staying at my summer place and I had some trouble with the internet connection, so I wasn't able to record this using Zoom. But anyway, let's go. So I'll start by sharing screen. And, here we go. So today I will talk about the timing of events and what is observed and what is not observed typically. And then I will talk about something a little bit different. It's sort of a follow-up from my earlier talk, and this time it concerns endemic models or endemic situations, infectious diseases that are present in the community for a long period of time. Then you have to think a little bit differently, and it's much harder, so the results will be more on the heuristic level. First, a few more words about the basic reproduction number. Arguably, this is the most important quantity of all for infectious disease modeling. Both me and Mikael talked about this earlier. And if you remember, it is defined as the expected number of individuals that a typical infected person infects during the early stage, meaning that nearly everyone is susceptible. It's important to note that R0 depends not only on the infectious agent, but also on the community in which it spreads. I think that is often forgotten. Many people talk about what is R0 for COVID-19. I think the question should be what is R0 for COVID-19 in Stockholm, or what is R0 for COVID-19 in London, or what is R0 for COVID-19 in Norrbotten in northern Sweden. I think the answers are different there. Probably the most important quantity was whether R0 was smaller than 1 or larger than 1. And if it is larger than 1, then there is a risk for a big outbreak, whereas if it's smaller than 1, this will not happen. So on the next slide comes some estimates of R0 for some specific diseases, but also specified in which communities the estimates rely on, and also which time periods, because this will change also over time, at least over longer periods of time. And it comes from what you might call the Bible of infectious disease model. It's written by Roy Anderson and Bob May, now Sir Roy Anderson and Lord Bob May. Maybe the text is a little bit small, but hopefully you can see. So it's some different diseases here: measles, mässling in Swedish, pertussis is called whooping cough, kikhosta, chicken pox is called vattkoppor, and I can't go through all. Rubella is röda hund, polio is polio. You see that the estimates are not go down, so it's ordered in the declining order. So the most infectious disease around, I think it's considered to be the most infectious disease of all infectious diseases, measles. It has a basic reproduction number which varies between different areas, also different time periods, but we see that it seems to be around, well, let's say 11 up to 18 for all parts except Kansas. So what's particularly with Kansas, I've never been there, but I think it's a remote state with not many people living there. So whenever the population or the community is has low population density, that will typically make R0 smaller. So the more densely populated area, the bigger typically R0 is. And we see that it is the order 10 to 20 or 10 to 18 here, but for other diseases it's lower, between 5 and 10. So a question then is the following: why are all diseases on the previous list have R0 larger than 1? You see there are no estimates which have R0 smaller than 1. I think there are For instance, I would think that for COVID-19 in Norrbotten, I think R0 might actually be smaller than 1, or at least in the rural areas of Norrbotten. Maybe not the towns. For instance, I heard yesterday that the Gällivare has an outbreak of COVID-19. But I think if you live in the rural areas of northern Sweden, I think R0 is actually smaller than 1. But nearly always you have R0 bigger than 1. Why is that the case? That's something, if you want, we can discuss on the live session on Thursday. So now, a bit of new things. It has to do with timing events and terminology for this. So there are a lot of different infection-related events occurring in time. One thing is the infection time. That is the calendar time when someone gets infected. So if I get infected today, June 18, my infection time is June 18. Typically, this is unobserved. This is nothing you know. Then we have a reporting time. So suppose I get infected today, maybe 1 week later, I start feeling ill. So that would be June 25. And maybe 3 days later, I go to a doctor. And then that is my reporting time. So that would be June 28 would be my reporting time. And then I have an onset of symptoms. The date for onset of symptoms in my description, it was June 25. And this is often observed, and the same with the reporting time. So these dates are typically observed, but not for everyone, but for the people seeking medical help. So these 3 things are in calendar time, but then we have some durations or periods. And the first one is called the incubation period. And that is the time between getting infected and showing symptoms. This is nothing you observe because you don't know when you were infected typically. Another duration is called the latent period. That is the time between that you get infected and that you become infectious. For instance, if we heard about SEIR models, said that first you were susceptible, then at some stage you got infected, you're called exposed or latent, but then after an additional time you become infectious. So the time in the latent state, that is the latent period. This is also unobserved since you don't know when you get infected, and typically you don't know when you start becoming infectious either. And then there are 2 time points that are relative to individuals, the infector and infectee, and I will talk about that later, but let me first describe, write the plot for these different things. So I think I then have to unshare, I'll stop sharing, and then I will share my whiteboard. And then I will try to write these things, and you have to forgive me, I'm not very good at doing this writing here. So here we have calendar time, and then a person might get infected here. So the person gets infected here. This is the infection. Maybe here the person becomes infectious. Sorry, I'm not writing very well. And here the persons have symptoms, onset of symptoms. And then maybe here the person infects someone. But that's, I'll talk more about that later. And maybe here we say that stop of symptoms. Maybe here it is stop become infectious. So these are all time events, and then we see how about the durations. This thing here, that is the latent period. Oops. Okay, I see. Here we have the latent period. This thing here, this is called the incubation period. It could very well happen that the order of these two are different. It could be that you have onset of symptoms before you become infectious. But I think it's more common to have it this way. And here is this is called the symptom period. And this here thing is called the infectious period. Also, these things can be have opposite order. I think maybe it's more common to actually have opposite order, but it's a little bit unclear when you stop becoming infectious. Of course, it's not a sudden stop, but it's a decline. So this here is still a simplification of the real world. But anyway, these are the type of durations we're talking about. All right, let me go back to my slides. And generation time and serial interval, that is connecting two different individuals, the infector and the infectee. So now I'll talk a little bit about generation time. Some part of this is based on a paper by me, which is detailed in the course webpage. It's a little bit technical for this level, but you're welcome to have a look at it anyway. So a very important property beside R0 for the dynamics of an infectious disease spreading in a community is called the generation time. It is denoted by capital G. So G is defined as the time between getting infected and infecting someone else. So in the hand drawing I did, there was one infection time, and that was there was one generation time, and that was the time between in the infection time and the up arrow when I said that the person infected someone. As a consequence of this is that if you infect more than one people, you contribute more than one infectious generation time. And if you don't infect anyone, you don't contribute with any generation time. It is clear that all generation times are not the same. So you can think of G as a random variable describing how they typically behave. Some are short, some are longer, how much do they differ in time, and so on. So the generation time, as opposed to R0, which is a real number, the generation time is a random variable, and you describe a random variable by its distribution. So for instance, maybe you think that the generation time has a normal distribution, but more common is to assume that it follows a gamma distribution. If you don't know what the gamma distribution is, you can look that up in Wikipedia. Both the normal and the gamma distribution have two parameters which can be chosen to be parameterized according to the mean and the standard deviation. So a common assumption is to assume that the generation time follows a gamma distribution, and then it remains to determine what is the mean of the gamma distribution, what is the standard deviation of it. Here comes a very simple toy example, not claiming to be realistic, but anyway, I will try to show a point. Suppose that R0 is 2, so on average you infect 2 people. We're in the beginning of the outbreak, so we can forget about people getting there's a big immunity in the community. And let's assume that you infect, actually, everyone infects 2 people, and you infect 1 person after 1 week and a second person after 2 weeks. So weeks is our time unit. This implies that the generation time distribution is defined by 50% of the infections happen 1 week later and 50% of the infections happens 2 weeks later. So what is the mean of this generation time? Well, that's an easy answer. The mean is 1.5 because it's either 1 or 2 and they're equally many of 1 and 2s, so the mean is 1.5. What is the standard deviation? I won't go into that, but actually the standard deviation is 0.5, and the reason that this is so easy to determine here is that the mean is 1.5 and all possibilities, being 1 or 2, have distance 0.5 from the mean. So the standard deviation is 0.5 weeks. So here comes a handwritten plot of what will happen with this epidemic. So there is no randomness here, unrealistic, but let's do that. So you start so this is week 1, week 2, week 3, week 4. You start with 1 person infected week 1. This person infects 1 person at week 2, and it infects 1 person at week 3. But at week 3, also this individual infects 1 person. So in total, there are 2 persons infected here. Week 4, there are 3 persons infected. This person infects 1, and these 2 persons infect 2, 1 each. And here, week 5, there are actually 5 people getting infected, 2 from these 2 guys, and 3 from these 3 guys. And then it goes on. So how many get infected different weeks? It's 1 person, 1 person, 2 person, 3 person, 5, 8, 3, 13, 21. So the number of people getting infected here, let's say, is how many were there here? There were apparently 21. And how many were there here? 13. So the number of people getting infected here is 13 plus 21. So that is 34. Maybe some of you recognize this series of numbers. It's called the Fibonacci numbers. And actually, it comes from a model for giving birth to rabbits, I think. So a little bit different, but still it is in this spirit. I want to explain it in detail. In the bottom row, I have listed out of the people that are infected this day, how many were infected by people infected 1 week earlier. So here in total there were 13 people infected, 5 from here and 8 from here. So here I have listed how many of these people that were infected by these guys 1 week earlier. And I have plotted this number, which was 8. I've marked that fraction with a black part of the bar. So we see that the black part of the bar actually makes up more than 50%. So here we have 89 in total, and 55 of them were infected by people 1 week earlier. I'll come back to this. I tried to argue that the generation time is an important property because it determines the speed of the epidemic. And if you're a statistician, the speed is something you observe. So from that reason, it might be possible to estimate the generation time, but it turns out to be not that easy. I will come back to this on my next lecture. But for now, suppose that we want to estimate the generation time distribution. How do we do this? Well, unfortunately, it's not possible just to look at the speed of the epidemic. Instead, what you do is you do what's called contact tracing, and that is that you find some infected cases, and you try to find out by whom and when they were infected. This has been done for COVID-19. Our study, which is I referred to earlier, is a few years old, and that study was considering mainly the Ebola outbreak, which took place in West Africa. And their contact tracing is easier because the symptoms for Ebola are very obvious, so it's easy to know if you have met someone with Ebola type symptoms. Anyway, that is the idea behind contact tracing. You find infected cases and you try to find out when they were infected. So from this, you obtain some observed generation times, let's call them G1 to GK. And if you have observations from a distribution, then that allows you to estimate the distribution. However, in this situation, there are some problematic things. Even if I think this is quite often the only way, there are some problems with this that you have to take into account when you do your estimation. I will talk about some of these, but not all of them. One problem is that the generation time was defined as the time between getting infected and infecting others. But when you contact trace, you look backwards in time rather than forward in time. So is that problematic? The answer is yes. I will explain why later. Another problem is that if you do this contact tracing, sometimes you find that there is only one certain infector, maybe 7 days ago. If it's COVID-19, you met maybe your uncle 7 days ago and he was coughing heavily, so then you expect that this was the time when I was infected 7 days ago. But in other situations, there might be multiple possibilities. So you said, maybe I met my uncle 7 days ago, but also I met my cousin who was also coughing, and this was 10 days ago. So what do you do then? Which is the generation time? That's another problem which happens in reality quite often. Another problem is that what you don't, as I tried to allude earlier, typically what you observe is the onset of symptoms and not when you get infected. So there's a delay. You would like to see the infection time, but what you typically observe is the onset of symptoms. So there is a delay here. And another problem has to do with representativity. And if you identify some cases, most likely the cases you will identify are severe cases because they are the ones coming to the hospital, so they are the ones you will reach. Whereas mild cases would not come to the hospital, they would not be registered. So if their generation times differ between as compared to the severe cases, you will estimate the generation time only of the severe cases. So let's start with the first problem, looking backwards. So as I said, we have the Fibonacci numbers, and actually the ratio of this over that is called the golden ratio, but I will not talk more about that. So if you contact trace, suppose you would do it here, probably it would have evolved much longer than this, but suppose you would contact trace at week 11, so you would find some people who got infected week 11, and you would ask them, by whom were you infected, and they would say, I was infected by someone here or someone here. And it's obvious from this drawing that if you pick a random sample here, there will be more people. You will pick more people from here than from here. And these people, they will say, I was infected by someone last week. And these people will say, I was infected by someone 2 weeks ago. So if you pick let's say if you pick 10 from here and 20 from here, the mean will not be 1.5, but it will be smaller than 1.5. So the mean, when you contact, the true mean we said was 1.5. The true mean generation time was 1.5, but when you contact trace looking backwards in time, the mean will be smaller than 1.5. And the reason for this is that there are more people infected 1 week ago than there were 2 weeks ago. So for that reason, more of the people infected this week will have its infector having been infected here as opposed to here. And if you don't take this into account, you will underestimate the mean generation time. And as I will explain in my next lecture, this has the implication that if you use these generation time estimates to estimate the basic reproduction number, you will also underestimate the basic reproduction number. The second problem that I mentioned, or possibly it was the third, was that what you observe is not the infection times, but you observe the onset of symptoms. And the generation time was defined as the time between infection times of an infector and its infectee. So this usually you don't observe, but what you can observe is the serial interval. That is the time between onset of symptoms of the infector and the infectee. So here comes a picture. So here we have time. Here's the infector getting infected. Here it's the onset of symptoms. And then here it infects the infectee. And this infectee has a shorter shorter incubation time before the onset of symptoms comes. So in this drawing, this is the generation time. And this is a serial interval. It's a time between onset of symptoms of the two individuals, and this is the time between the infections of the two individuals. So from this figure, it's clear that the serial interval equals the generation time plus the difference of the two incubation periods. Here we just do the same thing. So the serial interval is the generation time plus the difference between the two incubation periods. So if, for instance, the incubation times are independent, and if they're also independent of the generation time, this is not always true, but what I still say is nearly always true anyway, then it can be shown that the mean of the serial interval equals the mean of the generation time. So the two means are the same. E is for expectation. The reason for this is that here we have two incubation periods, and there is no reason to believe that the infector has a shorter or longer incubation period than the infectee. So the mean of this difference is 0. So the two things have the same mean. However, the serial interval is the generation time plus some additional randomness. So the variation or the standard deviation, the variance, but also the standard deviation of the serial interval is larger than that of the generation time distribution. This means that if we estimate the generation time, which we don't observe typically, if we estimate it by the serial interval, we will overestimate the variance. So if we collect data, it will be from the serial intervals, and we will look at the variance of these between these serial intervals. So we will estimate this thing, but we would have wanted to estimate this thing. So we will overestimate the variance of the generation, or over-predict if you want. This will have the same effect as the previous problem in when we use generation time to estimate the basic reproduction number. It will imply that we will actually underestimate the basic reproduction number. My final problem that I plan to discuss was this, when you're exposed to the disease several times, so you call it multiple exposures, meaning that you don't know exactly who infected you. So here is one case. This is when the person had onset of symptoms, and then you ask the person, have you met anyone with COVID-19 type symptoms? And this person says, yes, I did. I met someone 7 days ago and another one 10 days ago. This one says, I met one 6 days ago, 5 days ago, 6 and 8 days ago. Here we had 5, 8 and 10 days ago. So some of these, there is a unique infector, but for others, there are multiple possibilities. So the question is, what do we do with this type of data? If you, one easy solution is to throw away the ones with multiple possibilities, just keeping the one where you have a unique infector. A problem with, and this has been done, it was done in the Ebola study that we looked at. So actually they threw away 75% of all the observations, and that's usually not good. But also there's another problem here, that the remaining ones will be biased. It is easy to show using a mathematical model or a statistical model that if you throw away the ones with multiple infectors, possible infectors, the ones that you keep will typically be shorter. The reason for this is that if you have a very long time between infection and onset of symptoms, it's more likely that you will have met another person having COVID-19 symptoms than if you had a short time to onset of symptoms. So for that reason, you will also, those intervals, if you throw away the ones with multiple, the remaining ones will be biased from below, and this will imply that also here you will underestimate the mean generation time. And as a consequence, which I will explain in my next lecture, it will have the effect that you underestimate R0. So all these three problems have the same direction in the effect, that you would underestimate the mean generation time, or in one case overestimate its variance, and the consequence was that you would underestimate R0. So we looked at this an Ebola paper, and as I said, they threw away 75 of the observations, and the combined effect of these three problems we estimated to be that the estimate of R0 was underestimated by about 23%. So a fair amount of underestimation. For COVID-19, we did the same thing. That has not been published. The problem was that there was not enough information. It was done a quick study, so they didn't explain. The only thing we knew was that they were contact tracing, looking backwards in time, but we did not know anything about multiple exposures. So if we only took the looking backwards in time, we believe that the estimate of R0 was underestimated by about 12%. Okay, so that was about the generation time, where I was involved a little bit in that study. So now some more general stuff. It's important to have in mind that people that get infected get different type of responses. Some have very severe symptoms, and some even die. Others have very mild symptoms, and some people that get infected show no symptoms at all, but still they could infect others. So quite often you categorize individuals into severe cases, mild cases, and asymptomatic cases, but you can make an even finer grid of symptom levels as well. And it's important to have in mind that there is a bias in observed cases towards the severe cases. You usually hardly ever observe these. Sometimes you do some sample surveys, you might find some of them, whereas the severe cases, you typically observe all of them. So this is important to keep in mind, that among the observed cases, there is higher severity than among cases in general. This can also have the effect that you estimate the probability of dying incorrectly. the most interesting quantity is called the infection fatality risk. I see it says fatality, but it should be fatality risk here, and that's called IFR. So the interpretation of this is, if you get infected, what is the probability of dying? For COVID-19, that is believed to lie between, let's say, 0.3 and 0.8. I think 0.5 or 0.6 is a common estimate. However, if you don't keep this in mind, that your observed cases are more severe, and also it's easier to estimate what is the probability of dying among the reported cases. So that is called the case fatality risk. But from a spreading point of view, and also from, I think from a human point of view, the more important quantity is the infection fatality risk. But it's important to keep distinguish these two things. And what I've already alluded at is that for nearly all infectious diseases, not only COVID-19, but for most infectious diseases, the number of reported cases is very small in comparison to the number of infected cases. For instance, for influenza, the number of reported cases of influenza each year, I think, corresponds to definitely less than 10%, probably about 1 or 2% of all people getting infected from influenza. So there is a substantial amount of under-reporting, and this is a very important thing to have in mind, and it's a hard thing to estimate. We know what fraction that have been reported, but it's much harder to know how many that have not been reported. One way to do this is by testing individuals from a random sample, and I think this has been used too little during the COVID-19 epidemic in Sweden. So you pick random samples in the community and you test if they carry the virus or if they carry antibodies indicating that they have been exposed to the disease earlier. So this is my last slide before a break and the end of this recording. So I think there will be 2 home assignments during this course. The first home assignment has not been produced yet, but that will be common for all. Whereas the second home assignment will be done individually. So you should try to think of what could be an interesting project. And I think there are several interesting projects in connection to what I talked about, the generation time. So for instance, you can try to find out numerically by means of simulations, different thing. How big is the difference between the true generation time distribution and one that's estimated from contact tracing if you do some simulations? How would you do if you have singular multiple exposures, not infections? It should be exposures here. How big is the effect of throwing away cases with multiple exposures and so on? And you could also add some additional thing. Suppose you have symptomatic and asymptomatic cases, and maybe a fraction of the symptomatic ones. So you have a model, you say that with probability P you become symptomatic, with probability 1 minus P you become asymptomatic, and then probably the symptomatic people infect more than the asymptomatic ones. Maybe their generation time differs, and then you collect data from the symptomatic to symptomatic infections, and from that you try to estimate the generation time distribution, and you would like to compare that with the true mean generation time distribution. Sorry for the typos here, I saw several typos here. So that is one possibility for doing different types of home assignments relating to generation time. Okay, with this I will end the first part of lecture 3. Let's see now how I do that. I should stop sharing, sorry. All right, thank you very much.